Types of intermolecular forces. On to London dispersion forces. They occur between all molecules. They result from the fact that electrons are always in constant motion, and sometimes they're on the same side of the molecule. So let's look at the picture down here. Two electrons, and instead of being equally spaced around the nucleus, here's your nucleus right there, they're both on the same side. So we now have a polarized molecule. One side is negative, that's this side, and the other side is positive. Now, since this doesn't occur all the time, because just as easily as the electrons are over here on the left, they can move back to the right, you have something called a partial charge. It's called partial charge because its average value is less than your standard charge, your elementary charge, 1.6 times 10 to the minus 19th coulombs. So we label that as delta negative, delta minus, and then delta plus. And that is the partial charge. This polarization, this molecule over here, was polarized by the random movement of electrons. If that's near another molecule, it's going to polarize them because you have a slight positive charge here. So the molecule over here, the electrons will get attracted there, leaving it with a delta minus and a delta plus on the other side. And then once you have plus here and minus here, you have Coulomb attraction. So the polarization creates an electric field. This molecule is creating an electric field that oppositely polarizes this molecule, and then you have an attraction between the delta plus and the delta minus of each molecule. Let's see what happens with helium. It has two electrons, and you can see the two electrons back there, and then the 2 plus right there. That, of course, is your nucleus. Normally the electrons repel each other, but every now and again they wind up on the same side. So that's going to give us a partial charge, partial negative charge on the left, and a partial positive charge on the right. So we have a polar atom, we have an excess of electrons on one side, and a shortage on the other. Let's bring in a second helium atom over here. What happens is that gets polarized by the first helium atom because the first helium atom has a slight positive charge, a partial charge on this side, so it will attract the electrons from this helium atom to this side. So now we have a net positive here, a net negative here, and we get an electrostatic attraction. The London dispersion forces, or just called dispersion forces, are attractions between an instantaneous dipole, that's this guy right here. The first helium atom is the instantaneous dipole, and the induced dipole is the second helium atom, where its polarity was induced by the first helium atom. The London dispersion forces are present in all molecules, whether they are polar or nonpolar. All molecules will emphasize that there. The tendency of an electron cloud to distort in this way is called polarizability. Because larger molecules have more electrons, they are more polarizable. Not too good with that word. Molecules with more electrons experience stronger London dispersion forces. They have more electrons to polarize, you can get greater partial charges, and then the forces between the molecules will be much greater. Let's check that statement out with some real data. We have the halogens over here, and then we have the noble gases. We have those two families. And we show the number of electrons in each molecule. So we have fluorine 2 has 18, all the way down to iodine 2 with 106. Note how the boiling point increases. That tells us that the intermolecular forces are greater. They're holding the molecules together a lot closer, and they don't want them to boil. Same thing happens with the noble gases. More electrons, higher boiling point, which reflects a greater force. So the greater the number of electrons, the more polarizable the particles are, which results in stronger London dispersion forces and higher boiling points. Just as London dispersion forces increase with the number of electrons, they also increase with surface area. The greater the contact area between the two molecules, the greater the London dispersion forces. So here we just have this area here between these two molecules, not so big, between the two CH4s. Now down here, where we have this long carbon chain with hydrogens, look at how big the contact area is. So this will have a higher London dispersion force between the molecules than the two CH4s. Let's compare the two types of intermolecular forces, or van der Waals forces, that we've covered so far. We started with the dipole-dipole forces, and those are your permanent dipoles. They're polarized permanently. So if we have two polar molecules and they have the same size, roughly comparable, dipole-dipole interactions are the dominating force. However, if one molecule is much larger than another, dispersion forces will likely determine its physical properties, and that's the London dispersion forces. If the molecules are nonpolar, then dispersion forces will dominate, since all molecules experience dispersion forces, but not all have the dipole-dipole forces. We're now going to examine the third type of intermolecular force, hydrogen bonding. The graph to the right shows the boiling points for 4 polar and 4 nonpolar compounds. For the nonpolar series, that's the one down here on the bottom, boiling points increase with higher number of electrons. There are stronger dispersion forces due to the greater polarizability, so your boiling points will go up with greater numbers of electrons. That's because hydrogen is a very special case. The dipole-dipole interactions experienced when hydrogen is bonded to nitrogen, like this, or to oxygen, like this, or to fluorine, and we don't have fluorine there, but you can imagine it's the same thing, they are unusually strong. And then you will form these bonds here. See the dashed lines? Those are the hydrogen bonds. Part of the reason for the strength of the hydrogen bonds arises because of the high electronegativity and combined with the small radius of nitrogen, oxygen, fluorine. When hydrogen is bonded to one of these very electronegative elements, the hydrogen nucleus is exposed. So you have this large partial charge here on the hydrogen side, the delta plus. And you have a picture here of the various hydrogen bonds in the water molecules, and you can watch an animation here about hydrogen bonding. Thank goodness for these hydrogen bonds in water, because if not, there wouldn't be life on Earth as we know it. Because water is the only substance that is less dense in the solid state than in the liquid state. Therefore, solid water, or ice, icebergs, etc., float on liquid water. Here's a little penguin here on top of a little ice floe. If it didn't, life would be very different. Lakes would freeze from the bottom, because frankly, if the ice were heavier, it would fall to the bottom, and then as the winter got colder and colder, more ice would form on top of it, and fish wouldn't survive. But we have lakes freezing from the top, so fish can survive in the very cold water underneath the ice, but still they're not frozen. Hydrogen bonding creates the space in the ice that explains its low density. And here's another cool animation of the water-ice transition. Hydrogen bonds play an important role in polymers, both synthetic, plastics, and natural, proteins, RNA, and DNA. So here we show the hydrogen bond between this molecule and this molecule, and it stabilizes the secondary structure of proteins. So here we have a protein, and here's our hydrogen bonds over here. You can hopefully see how the protein is folded, but what's keeping these two chains together are these hydrogen bonds. Hydrogen bonding is the basis of base pairing in nucleic acids, RNA, and DNA. DNA is stabilized by 10 to the 7th to 10 to the 8th hydrogen bonds in each molecule. What a huge number. So here's your nucleic acid bases, okay, thymine, adenine, cytosine, guanine, and they are stuck together by these hydrogen bonds. So here's a picture of a DNA molecule, and where are the hydrogen bonds? Right in here in the middle, which help hold the two different chains together. There is a fourth intermolecular force between ions and molecules that will be important as we talk about solutions a little later in the course. ion-dipole interactions are not a van der Waals force. What these forces do is they cause ionic substances dissolve in polar solvents. Water is a polar solvent. So let's look at the picture on the left. This is an anion right here, negatively charged. And you can see how it's attracting the positive ends of these dipoles. So that's the anion dipole attractions. And then over here, you have a cation, positive, and that's attracting the negative sides of these dipoles. Here's a handy chart to see which forces are involved, the intermolecular forces. So we're going to start at the top, and first of all, are there ions involved? And we'll go down the yes track. So if we have yes, the next question is, are polar molecules and ions both present? Well, let's take the no this time. In that case, you just have ionic bonding, not covalent at all. You have sodium chloride, potassium iodide. If they are, if you have a polar molecule and an ion, and that's the yes track, then you have the ion dipole forces, like salt in water, and salt breaks up in water, okay? We talked about that on the previous slide. So let's go to the left. No ions involved. Now we have to say, do we have polar molecules? If not, then all we have are the London dispersion forces between the various molecules. If yes, we have another question. Are hydrogen atoms bonded to nitrogen, oxygen, and fluorine? Well, if they are, we have the special cases of hydrogen bonding, which is right down here. If not, we have dipole-dipole forces. So here, with the check marks, are our van der Waals forces, and here are the ion dipole forces, and here we just have ionic bonding. Another way to look at the intermolecular forces. Some people like flowcharts, some like tables like here, and others may like clicking on this red box down here to see another summary. So let's talk about the strength first. We go from weakest to strongest. So London dispersion forces are the weakest, and hydrogen bonding is the strongest. Next, what types of molecules do these forces apply to? London dispersion forces, all molecules. Dipole-dipole, only polar. Hydrogen bonding, only polar when hydrogen is bonded to nitrogen, oxygen, or fluorine. Then when in doubt, look at the number of electrons. The more electrons, the greater the chance it's London dispersion forces. Given dipole moment, the bigger the dipole moment, the more likely it's a dipole-dipole interaction. And hydrogen bonding, well, you look for the bonds. Hydrogen to nitrogen, or hydrogen to oxygen, or hydrogen to fluorine. Name the intermolecular force that is most likely to occur between each pair of these molecules. So pause the video if you need be and take a look at them. And when you're ready with your answers, go on to the next slide. All right, let's start in the upper left-hand corner. We have a nonpolar here and a dipole here. This dipole will induce a polarity in the nonpolar molecule by attracting more of the electrons to the right side. So you have a negative here and a positive here. So you've induced a dipole. So that's dipole-induced dipole. Now, when you have two nonpolar molecules, well, that's what the London dispersion forces are. Over here, you've got a hydrogen bonded to an oxygen and also to a nitrogen. That means that you have hydrogen bonding. Over here, this is kind of straightforward. You have two dipoles attracting each other. That's dipole-dipole. And here you have an ion dipole attracting each other, so that will be an ion dipole bond.